So in the previous lecture, we were discussing what happens or how does a differential amplifier behave in the presence of mismatches. That is, one half of the circuit is no longer a perfect mirror image of the other half. So the component values will be different in comparison with the other half. So in that case, what happens to the different parameters? The parameters of interest which we were talking about were ADM, the differential mode gain, ACM, the common mode gain, and the third and important parameter ACMDM. And I said something very important in the previous lectures is that ACMDM is a measure of how symmetric the circuit is. Now, the moment the circuit is no longer symmetric around the axis of symmetry, we should expect ACM-DM to no longer be equal to 0. For a purely symmetric circuit, ACM-DM will be 0. The moment there is any asymmetry in the circuit, ACM-DM will be non-zero. Now, we will see some very interesting results for common, what we call this as the common source differential amplifier with current biasing. Okay, I also told you the name for this is source coupled differential pair. The source of the two transistors are coupled, so that's why we called it as a source coupled differential pair. We will see it's a very interesting circuit, and by the virtue of this current biasing, we'll see some very interesting benefits this circuit offers as far as differential operation is concerned. If you recall in the morning's lecture, we said the moment we have some mismatch in the resistor and the transconductance, then we said ACMDM, the differential gain at the output for common mode inputs, will be proportional or will be equal to the common mode gain times the fractional errors. So this is the fractional mismatch between the two halves. Delta R by R is the mismatch in the load or the resistance. Delta GM by GM is the mismatch in the input transistor. So that's the transconductor device that is mismatched. And an error in both of them translates to a finite ACMDM. And we saw that because for a simple voltage bias, so when I say voltage bias, the source is connected to a voltage source here. The VGS is fixed. When we do this kind of biasing, we just saw that ACM-DM can be quite high if your ACM itself is high, because your ACM-DM is nothing but ACM multiplied by the error. So for example, if I have a 5% mismatch, I tell you that I have a 5% mismatch in the resistance and 5% mismatch in the transconductance, then what do you think will be ACM-DM in terms of ACM? 5% mismatch in resistor and 5% mismatch in transconductor. Okay, it will be 10%, 1/10 of ACM. So it will be mod of ACM by 10. So you should expect 1/10 of ACM. And if your ACM happens to be very high, then ACM DM will also be significantly higher. The hallmark of a differential circuit is that it should completely reject common mode variations. So therefore, ACM DM should be as close to 0 as possible. But here we have a circuit, because it has a high ACM, when there is a mismatch between the input resistors or the parameters of the two halves of a differential pair, we are seeing a significant increase in this parameter, ACM-DM. That's one of the most important performance metric of a differential pair. A differential pair ideally should not at all respond for common mode inputs. Differentially, it should not respond. That's what ACM-DM tells us. But if you have mismatch, even a 5% mismatch, if your ACM is very large, it can translate to a huge ACM-DM, and that's a problem. So we'll see that in a current source biasing, how will this manifest itself? What will happen when you have mismatch with transconductors? How will that affect ACM, DM, and ACM and all those parameters? So first, before we start with the analysis, as I said, whenever we are analyzing a differential pair, in the presence of mismatch, we no longer drew half circuit. Okay, so we'll directly go with the AC model. So the small signal AC model here comes to this. So here, if you look at the circuit, I'm applying a differential input Vi by 2 and minus Vi by 2 to both the inputs, and I'm trying to find out what is the output voltage differentially. You should note some very interesting fact here. What can you tell about the currents I1 and I2 here? If I1 is the drain current through this, I2 is the drain current through this, can I say the sum of the two currents, if I apply Kirchhoff's current law at this node, the sum of the two currents I1 plus I2 is what? What is that value in the circuit? 0, right? Because the sum will be 0. If the sum is 0, what do you gather from this? I1 equals minus I2. What does this tell you? What is this telling you? I1 equals minus I2. What does it mean? Mathematically, I1 is minus I2, but what does it mean intuitively? If I say I1 equals minus I2, what does it mean? It means that, I mean, see, I1 is what? What is I1 here? I1 is the small signal increase in the current in M1, right? Current flowing in M1, it is the increase. What is I2 here? I2 is also the current flowing in M2. But if I'm saying I1 equals minus I2, what does it mean? From small signal point of view, what can you say? If I say the current in M1 is increasing, what should happen to the current in M2? Look at the sign, it has to decrease and decrease by the same amount. That's what this equation is telling us. It's a very interesting result. It tells by the virtue of this current biasing, the circuit is forcing, the current biasing is forcing in such a way that any increase in I1 should be exactly equal to a decrease in I2. And that's a differential operation, right? A differential operation says that the currents in both the arms should be 180 degrees out of phase. Now the question is why? I mean, I'm just telling you that if you apply a positive gate voltage here, I1 can increase. I'm saying if I1 is increasing, then I2 is decreasing. Similarly, if I say I2 is increasing, then what about I1? If I2 is increasing, then I should automatically say if I2 is increasing, I1 has to decrease. So that is naturally enforced by this current source. The current source is naturally enforcing that. So intuitively, if you see this, by virtue of current biasing, we are enforcing some kind of a differential operation already. When I say differential operation, what do I mean? The drain currents in both these MOSFETs or the small signal drain currents are already 180 degrees out of phase to begin with. And I'm getting a differential operation with that. That's a very interesting result. Now let's assume I ignore, or for example, for that matter, if I apply same inputs, first I'll explain intuitively, then we'll go into the mathematics of it. If I apply same inputs to both, I'm applying VICM here plus VICM here. So now both the gates are increasing. Both the gate voltages are increasing. If gate voltage is increasing, both the gates are increasing. Drain current can only increase, it cannot decrease, right? If your gate is increasing, source is same for both. I'm increasing the gate voltage. Both the drain currents can only increase. But this condition is always true, irrespective of what the signal is. As long as I'm applying a small signal at the input, this condition is always true. I1 plus I2 should always be equal to 0. But if I apply same input to both the gates, the circuit is saying trying to increase both the drain currents. But this condition is saying both the drain currents cannot be of same polarity, they have to be of different polarity. Then what do you think will happen to the currents? See, the gate voltage is trying to increase the currents, but the currents and both the currents are in same polarity. That's what when I say both are increasing. The only possibility is both of them have to be 0, right? Because otherwise you will be violating this condition. So the only possibility is I1 and I2 itself will individually be 0. So therefore, now even before we analyze the circuit, can you tell me what will be ACM for the circuit? ACM, what do you think will be ACM for the circuit? Even before analyzing, ACM is essentially I'm applying same input. I can say ACM is automatically 0. If ACM is 0, what do you think will be ACM DM? Which means both the outputs are not responding. ACM DM is automatically 0. That's it. So that's the advantage this circuit is giving me. The virtue of current biasing, even though there is small mismatch between the inputs or the load resistances, ACM and ACM DM will be 0. And that happens because of the inherent differential nature of current biasing. It enforces that any increase in I1 should exactly be compensated by a decrease in I2. That's how the circuit itself is built. The sum of the two currents has to be constant. So now we will go into the mathematics, which is very trivial math, because now you understood the intuition. Once you understand the intuition, we'll just try to fill the mathematics for it. So first I'm going to write, see here, now what I'm going to do is that first, the way in which we analyze the previous circuit, I'm first going to assume transistors are mismatched, resistors are not mismatched. So I'll assume the transistor GMs are GM1 and GM2. Ideally, the GMs are both supposed to be equal to some nominal GM, but now I can say GM1 is something like GM plus delta GM and GM2 is GM itself. So there is a mismatch between the two GMs. And delta GM upon GM is the fractional error. Now if I have GM1 and GM2, I'll try to find out what is the voltage gain, differential voltage gain for the circuit. So whenever I want to find a differential voltage gain, this is right now guys, I'm applying a differential input. I've come back to the circuit now. Common mode is, I've discussed common mode intuitively. Right now I'm discussing the differential mode gain for the circuit. So I need to find out if I want to analyze this circuit here, the one unknown here is the source node voltage. What does the source node voltage come to? If I know the source node voltage, then it's a common source amplifier. I can easily find out I know the drain current, the gate voltage, the source voltage, the drain current. Drain current times the resistance will give you VO plus and VO minus. So from that I can calculate the differential output voltage. So first I'll use the simple condition to find the source voltage. You can simply use this condition I1 plus I2 equals 0 itself. So I1 should be equal to minus I2. If I1 should be equal to minus I2, what is I1? I1 is simply, can I say it is simply GM1 times VGS1. I1 is GM1 times VGS1 and I2 is GM2 times VGS2. So you have one expression. So that's what I've written here. So GM1 VGS1 plus GM2 VGS2 should be equal to 0. Then the other equation that I have here is VGS1 minus VGS2. So if I see here, I can apply Kirchhoff's KVL, Kirchhoff's voltage law in this loop, right? So if you see the gate voltage here is VI by 2 minus Vs. So this is the VGS1. VGS1 is VI by 2 minus Vs and VGS2 is minus of VI by 2 minus Vs. So subtract the two. VGS1 minus VGS2 should be equal to VI. Okay, so that you can directly apply a Kirchhoff's voltage law in this loop and find that out as well. So the difference between the two VGS's, VGS1 minus VGS2 is equal to VI. So now you just have two linear equations and two unknowns. VGS1 and VGS2 are two unknowns. You can readily find them. Okay, but just use intuition. Just tell me, look at this, the currents have to be exactly, magnitude of the two currents should be same. Do you agree to that? Do you agree that the magnitude of I1 should be exactly equal to the magnitude of I2? Okay, that is something that's already the circuit is enforcing. If that is being enforced, what can you say about the distribution? If I tell you that this GM is GM1, this GM is GM2. Let me give you an example. GM2 is 2 times GM1. GM2 is 2 times GM1. Then what can you say about VGS2, VGS1 and VGS2? See, I1 is nothing but GM1 into VGS1. So think about it. I1 is GM1 VGS1. I2 should be GM2 times VGS2. If your GM is higher, the product is same. The product of GM into VGS is constant. So if GM is higher, then the VGS2 will be lower or VGS1 will be higher. Okay, so the product remains the same. So of course you can say it depends on the values of GM. The product is same. So from that you can intuitively say your gate to source voltage VGS1 should be proportional to GM2. Okay, GM2, and VGS2 should be proportional to GM1. If your GM2 is large, if your GM2 is very high, then VGS1 will be high. It has to compensate for it, right? The current has to be same. So from that you can say, so directly you can write, I can actually write, you can of course solve these two equations as well, but the equations also make intuitive sense. VGS1 will be equal to GM2 upon GM1 plus GM2 times VI. And VGS2, what do you think should be VGS2 in terms of VI? See, VGS1 is GM2, so VGS2 will depend upon GM1 with a minus sign. VI upon GM1 plus GM2. That's it. So these are the two expressions you will get. Of course, if you can directly solve these two equations and get the same results, but they make perfect intuitive sense if you look at this. So the currents has to be same. So keeping that in mind, you will get these results, and these results will make perfect sense, intuitive sense. The moment you know VGS1 and I1 is simply GM1 times VGS1. So if you see, it will be GM1 GM2 by GM1 plus GM2. I1 is simply GM1 times VGS1, and I2 again it is GM2 times VGS2. So it will be GM1 GM2 by GM1 plus GM2 into VI. Now look at this, the magnitude is exactly same. Both the currents are same. The only difference is in sign. They both are 180 degrees out of phase. So even though you begin with different GMs, I1 and I2 are perfectly differential. Both the currents are exactly 180 degrees out of phase. That's what you want in a differential amplifier. Okay, this was not the case when you biased your transistor using a voltage source. When you used a constant voltage biasing, that was not the case. There was clearly a mismatch between I1 and I2 itself. But by the virtue of current biasing, it is inherently enforcing both I1 and I2 to be differential in nature, meaning I1 and I2 are 180 degrees out of phase. Okay, so now I know what is I1, I know what is I2. So what is your V0 plus? If you're asked to write, so this is I1 here and this is I2 here. So VO minus will be minus of I1R. VO plus will again be minus of I2 into R, because I'm assuming the sign of I1 and I2 are in this direction. Okay, so then VO is simply VO plus minus VO minus. So that will simply be I1 minus I2 into R. Right now I assumed R as constant, so it is I1 minus I2 into R. So this term I1 minus I2 is what we call the differential current. So ID is I1 minus I2, the differential output current for a differential amplifier. So when you substitute it, you get I1 and I2 are same, so you will get 2 GM1 GM2 by GM1 plus GM2 into R. So that's your voltage gain if your GMs are unequal. If the two transconductances GMs are unequal, you get this expression for the voltage gain. Okay, you can quickly see if GM1 is equal to GM2, this term reduces to GM. Okay, if GM1 equals GM2 equals GM, then you get 2 GM squared by 2 GM. So that term will reduce to GM and the gain will reduce to GM times R. But if you have unequal GMs, this is the expression for the voltage gain, provided the current source is an ideal current source. The biasing current source is an ideal current source. Then you get an expression for gain that looks like this. This will be very close to, if I assume your delta GM is very small, if your delta GM is much smaller compared to GM1 and GM2, I can approximate it to GM times R into VI. You will get the gain very close to GMR times VI. Okay, so that's the differential gain in the presence of input pair mismatch. Now we'll calculate the ACM. I'm going to apply same input common mode VI here and VICM here. Both of them are exactly the same. Now the VGS1 in this case happens to be VICM minus VS, and VGS2 happens to be VICM minus VS. Okay, VGS1 minus VGS2 happens to be VICM minus VS. So then I'll simply use this condition, GM1 into VICM minus VS should exactly be equal to GM2 into VICM minus VS. Okay, with a minus sign, of course. There is a minus sign here. So I1 should be equal to minus I2. That condition is true even in this case. So by equating this, the only possible solution for this, the only possible solution that you will get, the second term will cancel out. You will be left with GM1 minus GM2 into VICM equals 0. Okay, so this is the term you will be left with. So if GM1 and GM2 are not equal, then you will have VICM. I'm sorry here. Yeah, I'm sorry. You should not have written this, but yes. So all I'm saying is that you can easily show that VICM is 0. In fact, you can show that by writing Kirchhoff's current law in this loop. What is VGS1 minus VGS2? What is VGS1 minus VGS2? So you can traverse in this loop. If you traverse in this loop, you can see that since it's normally VGS1 minus VGS2, no, it's not 2 VCM. It's not 2 VCM. See, look at it this way. So traverse this loop. If you are traversing this loop, first you encounter VGS1, then you have, this is VGS2. So you get VGS1 minus VGS2. So that's the voltage difference. See, if let V1 be the voltage here, V2 be the voltage at this point. So V1 minus V2 is the voltage difference, that is equal to VGS1 minus VGS2. But since both V1 and V2 are same, you get VGS1 minus VGS2 equals 0. So VGS1 is exactly equal to VGS2. Yeah. Okay. So now I'll directly use this condition. The condition is that I1 plus I2 should be equal to 0. If I1 plus I2 is equal to 0, you will end up getting a current condition which is GM1 plus GM2 into VICM minus VS should be equal to 0. Okay, VICM minus VICS should be minus this should be equal to 0. Since the first they are transconductor, your biased devices with a fixed current, so GM1 and GM2 cannot be 0. Therefore, your VICM will be equal to VS. The source node voltage will exactly come to VICM. So it will perfectly track VICM as it is. Of course, you can analyze this using common drain approximation. You can apply principle of superposition and find out Vs due to the first guy and Vs due to the second guy, you will get VICM. And that should also make intuitive sense, because if your drain currents have to be individually 0, the only other possibility is gate to source voltage has to be 0. If the gate to source voltage is 0, then the source voltage will exactly be equal to the input voltage, VICM. Okay, so from this, if I ask you what is ACM now, the drain currents are individually 0. I1 is 0, I2 is 0. So therefore, VO plus will be equal to 0 and VO minus will be equal to 0. Both of them are 0 even if the load resistors are mismatched. Even if R is not same, even if it's R1 and R2, VO plus and VO minus will be 0. So what is ACM for the circuit? ACM, common mode in gain for the circuit, 0. So even if both the halves are not symmetric, still, of course, you can't draw the differential half circuits and all that anymore, but still it will give you a 0 common mode gain. And that comes because of the virtue of current biasing. Current biasing enforces some kind of differential nature for the circuit to begin with. It does not permit these two currents to be non-differential. So I'll use that word. It only permits I1 to be equal to minus I2. So only differential current. So if this current I1 is increasing, I2 has to decrease. And that is being enforced by the constant current source. So ACM is 0. Therefore, you can show ACM DM is also 0. ACM DM is again VO plus minus VO minus divided by VICM. But since these both are individually 0, you will get this term also as 0 as well. Okay, so that's the interesting thing about this circuit with constant current biasing. I've compared the two parameters here. So if you take a voltage bias differential pair, ACM is still approximately equal to ADM, even though there is mismatch and all of that. They both were very similar, and that is very close to, if assuming the mismatch is very small, it is very close to your nominal values when the circuit was purely differential. But now you're going to get ACM DM, a finite ACM DM for this. ACM DM will be approximately, for this voltage bias circuit, very close to differential mode or common mode gain times delta R by R into delta GM by GM. Okay, so the gain, the fractional error in the resistor gets multiplied by this value. So ACM, if your differential mode or common mode gain is very high, you want to design it for a very high differential gain, then that will naturally ensure that your ACM DM will also be very high for a given mismatch. Okay. The added advantage, the main advantage of a current source biasing is that we just discussed, it automatically enforces a differential operation. Any increase in this current should be exactly compensated by decrease in this current, because sum of the two currents, I1 plus I2 is equal to 0. This condition has to be satisfied. So this automatically tells us I2 is equal to minus I1. If I2 equals minus I1, that's like a differential operation. They both are differential signals. I2 is exactly 180 degrees out of phase, the magnitudes are same, so therefore I1 and I2 are differential signals. So the differential nature of this is enforced by a constant current biasing, because of which your ACM will be zero, ACM DM will also be zero in this circuit. And that's the huge advantage of a current source biasing. Even in the presence of mismatch, it can still guarantee you a good degree of differential operation. Okay, so finally, I'll just consider the same circuit with a finite output resistance ROC. The moment we have a finite output resistance ROC, how to analyze the circuit? How to find ACM, ACM DM, okay, and ADM as well. All three of them, how do I find all three, ACM, ADM, ACM, and ACM DM for this circuit? So this is where I'll introduce this term called quasi-differential, meaning we are going to make an assumption that your GM is given by GM plus delta GM and GM2 is GM itself. This delta GM, the change in the GM or the difference between the two GMs is really much smaller than GM1 and GM2. They are so small that I can still treat this circuit as though it is close to differential. So that's called a quasi-differential approximation. So in that, what we are going to do, we are going to take this current source and resistance and split it into two currents, so I by 2 and 2 ROC. So this again, the reasoning we discussed, why is it 2 ROC? So the parallel resistance should be ROC. So you can split this current and draw the axis of symmetry. Once you draw this axis of symmetry, the only difference here is that, the only difference in this analysis that what we are going to do is that we will do the analysis of both the halves. We are going to do the analysis of both the halves. We will not ignore one of the halves. Okay, right? Keep that in mind. That's because the transconductors are different. So therefore, I need to capture that two different transconductors in the output gain. But I'm going to treat this like a near differential circuit, very close to a differential circuit. So I'm going to assume this node will be at AC ground. It will not be at ideal AC ground, but it will be very close to AC ground. So that's why we call it quasi-differential. So I'm going to assume that that node is at AC ground for differential inputs. So immediately, if you assume this node as a differential ground, so then you can directly solve this circuit. The circuit reduces to uh, two resistors R and R, and it's a simple two common source amplifiers with GM1 and GM2. I already derived this for a voltage source, fixed voltage biasing. The gain expression, differential gain. This stage will give you a gain of minus of GM1R into VI by 2. This stage will give you an voltage of plus GM2R into VI by 2. Take the difference between the two, you will get GM1 plus GM2 by 2 into R. This is very close to, because your delta GM is very small, very close to GM times R. So GM1, I'm going to write as GM plus delta GM plus GM upon 2, that will be very close to GM itself. So you get differential gain remains more or less the same. But now we are going to consider what will happen to the common mode ACM and ACM DM. So this ROC here, I think by now you should understand that every practical current source is going to come with a finite source resistance, finite resistance, source resistance, current source resistance. Okay, so one of you are asking, I wrote I by 2 and I by 2 here because your dimensions are not same here. Your dimensions are not same. Is it okay to assume I1 and I2 splitting equally, the currents splitting equally? As I said, for quasi-differential, you can assume. That's the quasi-differential. That's an approximation I'm making again. That's an assumption. Okay, that's an approximation. I'm assuming the currents are nearly the same, but it will not be same. In reality, it will not be same. The currents will also be slightly different. Yeah. So, yeah. Okay. So now the next step is, by now you understand what ROC represents here. ROC represents the output source, output resistance of this current source. Okay. So if you want to increase the current source, we discussed in the morning's lectures that in the previous lectures, you would go for cascoding. Cascoding will improve your resistance significantly. So that's what we have to do. But what is the disadvantage of cascoding? What do we lose if I go for cascoding? Voltage swing, right? Because you need more overdrive to bias the transistors. Okay, So you'll need more and more voltage swing to bias transistors. Any voltage that is spent for biasing transistors is a wasted voltage. Okay, that much is going to be eaten away in the voltage swings. Okay, so fine. So now we'll try to find out. No, yes, yes, obviously. So this one of you are asking, this node is at AC ground for different. Yes, I'm finding differential gain. I'm finding differential gain. That's why I assume that node to be close to ground. Yeah. The next step is to find the common mode gain. To find the common mode gain, again, what should I do? I should open circuit this node. I'll open circuit this node, but I'll retain both the halves. I'll retain both the halves. So I'm going to get a circuit that looks like this. So you'll have, I'll ignore R naught for the time being. So you have GM1 and GM2 here. So the first circuit will have a gain of GM1R. R is your load resistance upon 1 plus 2 GM1 ROC. Right? So this is like source degenerated MOS common source. So the transconductance becomes GM1 by 1 plus GM1 into 2 ROC. It reduces by this factor 1 plus GM1 into ROC. Similarly, for the next other half, your common mode voltage will be, both of them the sign will be same. Because it's common mode, the sign will be both negative. Because it's a common source, it's negative. So this one will be minus of GM2R by 1 plus 2 GM2 ROC. Now you find the common mode gain, so which is the average of the two. You will end up getting GM1 plus GM2 by 2 into R by 1 plus 1 R by 1 plus 2 GM ROC. Again, I'll make this approximation that GM is very close to GM1, 2 is very close to GM, and delta GM is much smaller. So this term will be very close to GM. And I'll also make another assumption that GM ROC is much greater than 1, which is not generally true because you want to design a current source with a very high output resistance. So this will be generally held true. So what you get here is GM and GM cancels out. You will be left with R by, uh, you will be left with R upon 2 ROC. So, okay, so GM1, comma 2 is nothing but GM. I'm just saying it's 1, comma 2 is GM of the first input pair transistors. That's it. It's just a notation. So GM of 1, comma 2 is the GM itself. Yeah. Now, ACM-DM is the difference between the two GMs, difference between the two output voltages. You calculate that, you're going to get GM1 minus GM2 into R by the same denominator. Okay. If you recall from previous problem, which we did for a voltage biased circuit, differential pair, what we noticed was the differential gain, there was no, this denominator factor did not exist. But now if you see, you have this denominator factor which is reducing ACM-DM by a huge amount because RO1, ROC can be quite large. So your overall ACM-DM is also reducing significantly. I can argue the same for the numerator as well, the ACM as well. I'm sorry. I can argue the same for ACM as well. If you see this expression, the first term, this I can approximate it to GM. So it is GMR divided by 1 plus 2 GM ROC. So compare it with a voltage biased differential pair. If you compare it with a voltage biased differential pair, the common mode gain was very close to GMR itself. Even in the presence of mismatches, it was very close to GMR. But now it is getting reduced by a factor of 1 plus 2 GMROs. It's getting reduced by a huge factor. So that's the advantage of current source biasing. It's reducing significantly. Same way, ACM-DM also, you can show that ACM-DM also reduces by a huge factor. So I've finally written ACM-DM in terms of, so if you see here, I've always written ACM-DM in terms of a fraction of, this is nothing but ACM. It's a common mode gain. It's normally a fraction of the common mode gain. So this is the fractional error in the transconductance times the ACM. To begin with, ACM will be much smaller in a current biased amplifier. And ACM-DM will be a small fraction of ACM itself. So therefore, ACM-DM will also be much smaller for a current biased amplifier in comparison to a voltage biased differential pair. So that's why a voltage biased differential pair is often referred to as a pseudo differential. It's not really differential, it's pseudo differential. This is the name for voltage biased. So let me probably show it in a different. Yeah. So this is more often referred to as a pseudo differential. Okay, so that's it for today's class. I'll just finally just sum up the facts here. So I have not analyzed for resistor mismatch, but that's a very trivial extension of what we did right now. I'll leave it up as an exercise for you to work it out. Everything you will get the same expressions what we got before. So for example, ACM, if you see the expression for ACM will also remain more or less the same. Everything will remain more or less the same. The difference in ACM DM will be the fractional change in the resistance multiplied by ACM of the differential pair, the current bias differential pair. So if you include both resistor and transconductor mismatch, your ACM DM will come to very close to, it will come to delta GM, that's the fractional sum of the fractional errors in both parameters times ACM. Okay, and in a current source biased amplifier, to begin with, ACM will be much smaller than differential gain. It will be much smaller than differential gain. On top of that, ACM DM will be a fraction of that, so it will be ACM DM will be much smaller than ADM. Okay, so that's it. So we'll start discussing about nonlinear behavior of differential pairs in the next lecture onwards.